Alright guys, here we are on 0654 paper 4.2 from winter 2019, and we're looking at question 9. Okay, we've got two trains. The trains are identical except one is painted black and one is painted white. Both have shiny surfaces. That's going to be important later, so please make sure we are reading all of the question. Okay, both trains are stored at a station on a sunny day. That sounds nice, right? State the method of energy transfer by which energy passes from the sun to the earth. Energy transfer, there are three. Okay, we have conduction, convection, and we have radiation. Now, if we're thinking about radiation, we've discussed about the connotation of the word radiation. Doesn't always mean radioactive stuff. Okay, radiation means passing using electromagnetic waves, and that's exactly what the sun is doing to us. It is shining those electromagnetic waves on us, infrared, ultraviolet, visible light, all this, basically the whole range of the spectrum coming onto us and heating us. Okay, same with the train, obviously, and that is radiation. Why is it not conduction and convection? Well, we could argue there is an element of both. Okay, however, the real issue here comes with particles. Okay, conduction and convection require particles. Okay, conduction and convection require particles. Radiation does not. Radiation can happen in a vacuum, and what we do tend to do is the space, but certainly between the sun and the earth, we think of as a vacuum. So it's traveling from earth to us. The only one that's possible there is radiation. Okay. 4 hours, the temperature inside each train is measured. Inside the black train is 40, and then inside the white train is 30. Okay, well, what's going on there? You should have picked up the key term here is black and white. Alright. Alright, black and white are the key things here. We know that black surfaces are good absorbers of radiation, okay, and white ones are good at reflecting. As such, the black surface is a better absorber of radiation, which means there's going to be a greater increase in the temperature. The white one might increase a little bit, but nowhere near as much. We're then asked, what would happen to the temperature inside the train painted white if the painted surface was not shiny? Now, this is important, okay? In order to be a really good absorber, we need our surface to be two things, black and matte. So what we're doing here, if we change one of those, okay, then we're changing the absorbance. We tend to think about color, okay, but we also have to think about the type of surface. So, if we changed our shiny surface into a matte one, spelled M-A-T-T-E, okay, then that means it's going to become a better absorber. Not as good as a black matte one, but certainly better than it was before, and that's all we're really being asked to compare here is the previous case to the current. Okay, temperature would be higher because the shiny surfaces are poor absorbers of radiation and matte surfaces are good absorbers. Okay, I think either statement would be enough here, but if you're not sure, write the whole thing. Okay, we're then asked to do a nice calculation. We've got a train of mass 450,000 kilograms slows down with a deceleration of 0.6. Okay, remember, I'm putting in here that this is the acceleration. I've got inverted commas. Don't worry about acceleration and deceleration. They are basically the same thing. The only difference is the direction of the force. If you're accelerating, then you might have a force to the right. If you're decelerating, you might have a force to the left. Okay, our equation F equal to ma for calculating the size of a resultant force is completely valid. F equal to ma, I've got, I need to know F. Okay, I've got M, I've got A, 270,000 newtons, big number. We're then taking the train with and considering its headlamps. The lamps have a power rating of 350 watts, P, power, and are operated with a potential difference of 75 volts, V. Show that the current through each headlamp is 4.7 amps, right? You know I, you know V, and you know P, so we need to think of an equation, all right? Our triangle P equal to IV, okay? PIV, I don't care how you remember it. Therefore, I is P over V, 350 divided by 75, 4.67, or 4.7 amps. I've then done this thing. This is kind of a bit of vanity keeping in. When I was younger, we were taught whenever you're proving something, you put in the letters QED. Can't remember what they mean? Go and find it out. It basically means I have proved it. It's a Latin phrase, okay? It means I've done it, okay? Proof questions are always nice because you should be getting the answer that they get, okay? If you get something else, you've done something wrong, not sure, have a stab at it, rearrange the equation, and try and recall how to link those variables. Okay, last one, combined resistance of the two lamps connected in parallel. Very difficult question, all right, because it does involve a bit more thinking. Why do we know that? It's a 3 mark, not a 2 mark. Start with the fact that they are connected in parallel, so that when we're doing in parallel, we are remembering this 1 over RT thing. We've got 2 resistors, we've got 1 over R1 plus 1 over R2 is equal to 1 over RT, where RT is the total resistance. Now, at this stage, okay, after we've written this down, we don't know R1 and R2. However, we do know that they are identical. They've both got a power rating of the same power rating, and they've got the same voltage, and therefore they are identical. So I can down here say that R1 and R2 are the same. I'm just going to call them R. All right. Well, I need to know the value of the R of each of the resistance. That's where I need to go for my equation that I know from Ohm's law, which is V equal to IR, or I remember my definition of resistance, which is the ratio of voltage or potential difference to current. Do I know the potential difference? Yes, it's up here, it's 75 volts. Do I know the current? Yes, it's 4.7 amps. And so therefore I can work out the resistance of each of those lamps individually, 15.95, which is basically 16. I then take this number and plug it right back in over here. 1 over 16 plus 1 over 16, 2 over 16. I then need to remember to flip it. If 1 over RT is 2 over 16, then RT is 16 over 2. 16 divided by 2 is 8 ohms. Okay. Can we check this? Absolutely. One safety check is remember that R, the resistance of the lamp, is 16. If we're taking things in parallel, then the resistance should decrease. Okay, so our total resistance is always less than the smallest resistance we started with. All right, so if we had R equal to 16, we're expecting a value less than 16, or 8, certainly less than 16. It's half of it, and so therefore we can be pretty confident we've done the right thing here.